Okay, hello everyone. Up next, we have Chris Miceli. Chris is a production engineer at Facebook in the live video infrastructure team, working on Facebook Live, building infrastructure tooling extensively in Python 3, as well as being particularly excited in the BPF work done by Brendan, Craig, and co., including the Python tooling around that. All yours, Chris.
Hello and welcome everyone. As was just said, my name's Chris Miceli, and today I'm going to talk to you about debugging systems using the new USDT probes, which have been introduced as of Python 3.6. Because everyone runs the latest, everyone's going to be able to run this now. And as was said, I work on our video infrastructure team. I work on the live streaming stuff in particular. We have a lot of support systems in Python, as well as Python throughout the Facebook infrastructure. So there's a lot of work around this to gain visibility. We're going to go into why we kind of use this sort of stuff throughout the talk. So yeah, let's just jump straight in. So I'd like to preface this talk by saying I am not the person that wrote it. I'm not like an expert, but this is something that I've spent a few months playing with, and I'm hoping to bridge that first learning gap. So there's a bit of a learning thing when you first get into it that you kind of want to know. Hopefully you can walk away from this and start using it. If not, chase me up afterwards and I'll help you out. I'd also like to say, unfortunately, I can't go over debugging this in Windows because I believe this isn't supported. I haven't come across it at all yet. I'm a Linux person, so I've had some Unix-based system stuff as well that I've been looking into for this sort of purpose. But most of this is concentrated on Linux, but will work across a whole bunch of operating systems. So to describe debugging as only two things is very, very simplistic, but I'm going to do that, otherwise I'm going to go over my time. So let's say that you've got two realms, one being the application level, which is your process with your code running in it. And when you're going to debug something like a Python program, you're going to look at things like the stack traces, you're going to look at logging, or the de facto, which is to stick a bunch of print statements everywhere, run it for a while, and then grep for them. Pro tip, you put your username at the start, and then you can just grep your username, and all the stuff you put in there, you can find it. But let's pretend you don't want to do this, and you're going to start looking into different ways. So the second way you can look at debugging as a problem is for a system. So a system would be the operating system it runs on with the context of the hardware and all the things underneath your program that you kind of get for free. Like you open a socket and voila, you have a network connection. That isn't how it works. Sorry if I'm breaking this news to everyone and they haven't heard that before. There's a bit more involved. So this system involves all those parts. So what we're going to talk about works for both systems and applications, but we are going to try and focus on applications because that's what we recently gained in the new Python 3.6. But this picture kind of encapsulates what I'm getting at. So you have each house as a program, and they have probes which have been injected into them. So you might have this particular house has been walked into, and that probe goes off and fires, right? So someone walked into that house. Then on its own, that doesn't tell us very much. However, you go along and you say, all right, well, this land underneath here cracked, right? So all the houses that happen to be on that land now are impacted, right? The very, very important thing that I'd like to kind of touch on here is the context around all of this is very, very important. So we're going to talk about garbage collection a bit later, and garbage collection very much depends on the state of the system, whether it is a very big problem, right? So we'll get into that more. So something I'd also like to point out is we're going to talk about tracing, so capturing these probes, and that would be what this picture is doing right now, right? So this picture is literally saying, okay, the land is cracked and the house was walked into, so whether they are related, we'll kind of try and find out. But that's what I'm trying to get at. Everything's kind of contextually important, and these are the pieces of the puzzle that we're going to be working with today. So again, I'm trying to distill the fundamentals of debugging here. It's only two pieces. It is creating data points that you can then use later on, and then deriving meaning from those data points, right? As I said, context is key. Just entering the house means nothing. If the land is cracking underneath it, then it might mean something. So these are all things that you kind of need to do. As far as this talk is concerned, what we are very interested in is what this means for us. One is adding probes, and then as I said before, it's about these traces, these programs which are kind of new now, but they will give us insight as to what is actually going on. So let's talk about collecting data, okay? So this is all going to be quite useless if we can't collect data, right? There are two kind of probes that exist out in the world. You have kernel probes, which is the state of the operating system, when you go and you're writing to block systems underneath, what's going on there. And then you have user land processes. So you've got garbage collection is the fantastic example for Python 3.6, which I like. I'm going to keep going back to that because I really like it. And these are the state of your application as it's kind of going along. So Linux gives you a bunch of these user land probes and kernel probes basically for free by running a recent kernel. So there are a good set of tools which exist. We are going to talk about those in a moment. These tools have a good starting set. So you could go to the BCC repository, for example, go through the tools section and find one-off tools and just kind of start playing and understanding what's going on from there. I keep saying USDT, and that is because if I try and say user land statically defined trace points every time, I'm going to end up standing here making a mess of my words. So what they are, paraphrasing from the dtrace website, they are these probes which are stuck into programs when inactive, cost very, very little. They shouldn't have any performance implications. However, when you do need to investigate how, say, the Python interpreter is running, you can jump into that very, very quickly and very, very powerfully by just basically turning them on like a light switch, right? So before Python got them, they'd been added to Java and Node.js in the past with very, very similar functionality for garbage collection, function, entry, and exit. And they'd also been added to important production systems that people run, such as MySQL and Postgres. And there are a lot of core libraries that are starting to get them now. So this is a developing area, but a notable one here is glibc has probes in it. I believe they're for malloc. But yeah, I think I could shoot myself in the foot and say the wrong thing. Doesn't matter. Over the last 5 to 10 years, that is when all this revolution to being able to trace these kinds of things has started to happen. I believe dtrace's release was in 2005. And since then, people have started adding probes all around systems. So this has kind of grown with the movement towards DevOps, SRE, production engineering. These are the driving forces of these sorts of probes and understanding of how a system is running. But if you look at how applications are being developed today, it is very, very different to how they used to be developed. These days you've got containers, you've got multiple systems, microservices, you've got, no one has one IBM mainframe that runs everything anymore, right? So it's a changing world, and this is trying to simplify that so you can see what is happening in a system. So what did we get with Python 3.6? We got garbage collection beginning and ending, and we got function entrance and exit. It sounds kind of boring, right? However, when you do have these function entry and exit, you have the file name, the line number which is being executed, the function name, as well as a pointer to the frame. So you have a lot of information that you can then use to derive meaningful, meaningful assumptions or things like that. But this is just the start, right? So from now, we can look at adding pull requests for different things that I think are kind of important. So two that I want to kind of highlight here today, while I've got the appropriate audience for it, is instrumentation around the GIL would be fantastic. It would mean that we can then see when there is some sort of contention in a system under synthetic or real production load. Obviously, you couldn't run it all the time, but we'll get into that later. And another one that is very, very important, and I've been burned by before, so I care about it, is library imports. Python lets you import a library whenever you want, right? And then on top of that, you have this concept of, there's a library called demand import, which allows you to lazy load your import whenever you kind of need it. The problem with that is you will be running your program, it'll be happily chugging along, and then there's this big pause. And that's because it's hit something that's like, oh, I need to import this library now, and it happens to fan out and import a whole lot of stuff. If you had probes for this kind of stuff, debugging it would be a breeze. You basically turn it on, you notice all these import probes come up, and you say, okay, this is happening because of these imports. They happen to be big, they happen to be doing whatever. So these are just two ideas that I thought of, but I'm sure there are plenty more. Whilst I do mention that there are a lot of probes which you could add here, please note that a lot of the subsystem of Linux, a lot of like helper libraries like glibc, things like that, they do have trace points already. So adding things which are basically doing the same thing can be problematic, not problematic, but you wouldn't duplicate it. A great example would be files. Like if you're opening files and you thought, okay, I'm going to add a probe for whenever I open a file or a socket or whatever, that is instrumented elsewhere, so you don't really need to add that to the Python interpreter as well. Things that are Python specific, such as importing and GIL, they are very, very useful for us. So I would highly recommend thinking of things that are very Python-centric, application-centric, and kind of like fanning out from there. So from there, we've gone and we've said, okay, we've got all this data, that's perfectly fine. Now, how do we analyze it? So anyone that's been watching this area very, very closely will have noticed that there are lots of tools trying to, I'm not going to say compete to be like the #1 tool, but there's a lot of action in this area. So I'm going to try and pick a couple that I'm a big fan of or I've used in the past and kind of distill them for you, give you an introduction, but just note that these aren't the only ones that exist. You're going to find them they're kind of everywhere. But that's the nature of a growing area. So without further ado, let's talk about SystemTap. So SystemTap is a language that we're going to go through later, and it will give you low-level access to the system because what will happen is your program will then get compiled into a kernel module that you can then inject into your system. So then it will have access to a lot of information as to the underpinnings of your operating system, as well as what's kind of happening. And that comes with its own set of caveats. The SystemTap community was how people did this on Linux for quite a while. There are more competing things coming out now. However, it is very, very actively maintained. They have a lot of sample code. They work very, very closely with the Linux kernel developers so they can adopt new things. They're a very, very active community. The only thing that I would like to kind of preface my recommendation of using SystemTap with is if you happen to be at a pinch and you said, okay, I have to use this right now, everything's on fire, SystemTap can be complicated to get started with. Whether that is just me or everyone else, I run Arch Linux on my personal laptop, and so I thought, okay, I'll just install it, pull down the package. Well, the package isn't maintained anymore, and my kernel is, a long way into the future, so I have to then compile it. Then running it wasn't necessarily easy, so I had to then look through all the documentation. It's just worth knowing that if the world is on fire, that is not the time to try and fire everything up. So just kind of experiment with these kind of things early is what I want to kind of, push everyone towards. So let's talk about eBPF. eBPF is the extended Berkeley packet filter. It's a virtual machine interface which we can now use to access some inner workings of the kernel. It was imagined in a 1992 white paper, which then we now built out for network filtering. That's what its initial purpose was, network filtering. It powers TCP dump is one of the notable examples, but I believe it may even be the underpinning of the libpcap stuff, but don't hold me to that one. So the whole concept behind this is we should be able to expose kernel information through userland, right? So you should be able to compile bytecode for this VM and get information out. It was expanded to include the entirety of the Linux kernel. Well, not entirety. They're exposed to more of the Linux kernel as of around Linux 4.1. And so anyone with a moderately recent kernel will have this built in. There is still a lot of work underway to build out this virtual machine, but it is very, very strong and very well maintained. So at this point, telling you about a virtual machine that you can't write code for is kind of useless. However, that's where BCC comes into the fold. BCC is a tool chain which has been written by the IOVisor community. It's an open source community. I believe it's now part of the Linux family and the open source foundation, sorry. And it contains two big pieces. The first piece is the backend, which allows you to write a piece of C that will get compiled to the eBPF bytecode. And then there's a front end to analyze this, which is written in, which you can access in Python or Ruby. But no one's going to do that here, let's be honest. So something I want to make very, very clear, when you first get started with this stuff, it is very, very tempting to think that BCC is eBPF. I got very, very confused to begin with. Just remember, one facilitates using the other, and then you'll be fine. So something I also wanted to mention was because the front end is going to be written, you're going to probably write it in Python, you have access to taking the data that you get out of the virtual machine and literally plug it into anything like, if you want to put it into StatsD, you want to put it into any reporting frameworks that you have, it is trivially possible. Also, I'd like to say that this BCC repository has a huge number of tools that have been example programs that people have need to run in the past, or the porting of existing programs which people have been using in the past to this new framework. And I've got a few that I've been using. So you've got exec_snoop, which lets you see programs which are being executed on your machine. You have BIO latency, which you can see the latency of block IO on your machine. And then you have something called file life, which lets you see short-lived files. I had a huge problem with that once, and this saved me big time. The biggest thing that I can say for these tools is that you can read them and understand them in about 15 minutes. And the reason why that's useful is you might say that, hey, this script is very, very close to what I want. I'm going to change a few different things, and for this very specific debugging scenario, which I'm currently dealing with, I can then figure out what's going on. That is something that you can't really do with a lot of things when it comes to debug. Like some tools you use are completely inflexible. I wanted to make it very clear that these are very flexible to whatever you want. So dtrace, and probably shouldn't be left to last, this is what actually started the whole revolution, really. When dtrace first came out, it won a whole bunch of awards. It was originally written by Sun Systems for Solaris. However, there are ports for the various BSD flavors, as well as Mac OS. So anyone with a MacBook now can use dtrace. As I said, it won a whole bunch of awards. Unfortunately, I can't do a dtrace demo. This isn't my MacBook. I use Linux. So unfortunately, I can't give you an example. However, I will say that when I did read all the documentation for the various traces, this one had the most documentation. And it is very, very easy to get started with dtrace if the documentation is anything to go by. And it's been used the most widely in the community. There was an unofficial attempt to port dtrace over to Linux. I'm not sure the status of that at the moment, but I believe most people are now moving towards eBPF. That's how fundamental to the game dtrace was when it first came around. So I've probably bored you enough with the theory of all this. When am I actually going to use it? Funny, we should mention garbage collection again. However, Instagram and Django, there was a big effort to understand what the memory footprint was. So this engineering article here is talking about how Instagram went through all the process of trying to understand what is happening with their garbage collection and basically turn it off. However, in the article, there was mention that they couldn't get enough information as to what's happening with garbage collection. which happens to sit very perfectly with this talk, because I can then produce you an example which we can then debug with two of the tools. So this is my de facto go-to example when I'm dealing with the USDT probes as they are today. So it is very advanced code, as you can see. You probably all understand it by now. However, we have a simple printer function. The reason we use this is because when I want to see function entry and exit, this is Python bytecode, and so I'll be able to watch that. And apart from that, all it does is print, sleep, and then force garbage collection. So like I can spend no time on that because there's nothing that exciting. This is SystemTap though. So SystemTap, as I said, is its own language. It reads similarly to pseudocode when you get to see running examples of it, but can be a little bit complicated and contrived to understand at first. So let's start. We look at CPython, which is my build of Python with the dtrace markers in it. We want to know when garbage collection starts. We're going to increment the counter. And then every 3 seconds, I'm going to say, hey, I garbage collected this many times. Believe it or not, the answer was 3. So eBPF, again, as I said before, there's a back end and a front end. This code might be a little bit difficult to read, but we can try and distill it very quickly. So the BPPF text, we have the import for ptrace. Then we have BPF table. That is going to be called counts. It is going to be a shared array, a shared dictionary between the virtual machine and our front-end code. That's just a macro, obviously. Then we have countMe. So countMe is the function which we are going to execute whenever we see the GC probe. Very, very interestingly named. Anyway, it will just increment a field in that dictionary, and that's all, okay? Then we have the front end of it, which is literally these are just concatenated one under another. It's not like there's any special importing going on. All we do then is we find the ability, we find the library with the Python markers. Then we look for, on the third line there, we enable garbage collection, and we say when this event happens, run this function, right? That's all that's happening there. And then we inject it, and then underneath that is probably the easy bit, where every 3 seconds we read this dictionary, pull the values out, and then reset the counter so that it goes back and says 3 every time. So I was going to put a slide here which had 3s all on it, but I think everyone gets the point. So the difference is that eBPF has more code, right? However, the difference between them is mainly in the implementations. One's in the virtual machine, one's a kernel module. And SystemTap, you have to learn an entire new language. You can get started with eBPF with knowledge of a little bit of C and reading through header files. And Python, but I didn't need to mention that here. So a couple of caveats. So the first thing is you can't run them all the time. They are expensive. So you will use them when the world is on fire and you want to know what's going on. So the second caveat is that the kernel and SystemTap are developed distinctly, so you can have version incompatibilities. That is more rare than the situation where you can't install kernel modules. There are a lot of people who can't install kernel modules for PCI compliance reasons, for example. It is worth noting that in those situations, SystemTap might be a little bit funny to get running. The last thing I want to mention is you want to know these before you need them. Yeah, if you have to try and calmly read this while everything's going terribly, you're going to have a really bad time. So with all that said, go and have a play, have fun. And if you have any questions, let me know. Otherwise, these are the best parts to get started reading. Julia Evans has had some very fantastic blog entries recently, and Brendan Gregg is basically, I don't want to say the godfather, but he's like the de facto person everyone is reading when they're talking about systems performance, and he's got a fantastic book on it too. And that's the repo that I've been talking about the whole time. If anyone has questions, please let me know.
Questions?
And you can come up at the end if you're nervous or worried that I won't know.
Nope.
Hi, Chris.
Hi.
You might know me. Are there security implications around this?
So yes, running anything as a kernel module on your system has security implications of some description. I imagine that in many cases people don't, like I would understand if a lot of people don't have root access on their machine, which means that they couldn't do this as well. So there is the like giving people access to do this sort of thing can be a problem. But generally running things inside your kernel that are arbitrarily compiled off a language someone wrote on the internet can be a bit of a problem. As I said, PCI environments are a fantastic example where you can't just run kernel modules because you feel like it. So the virtual machine could have bugs as well. There's always that chance. However, yeah, like you would be doing this in order to gain insight. I imagine that when you're reproducing this into a staging environment, those constraints are relaxed a little bit. If you've got shadowing environments, that's even better because people won't see this kind of thing. So yeah, there are security implications, but you know, that happens when you give anyone root on any box.
You didn't mention strace. Where does that fit in to the scheme of things?
So strace is a different realm of debugging this sort of stuff. That is the interactions with the system more than understanding how your program is doing. So I was attempting to talk just about the Python stuff, but then falls into like kernel understanding. strace is the interface. So you'll see like file opens and stuff happening through strace, but this is more about like giving you insight to the Python interpreter and what the Python interpreter is doing throughout the process of your system. Justin?
Is strace slower than eBPF?
That's a good question. I would have to run a sample, but I believe that it would be significantly slower. I don't know whether they are interchangeable is the other thing. So I don't know whether comparing them is apples with apples. So I can do that, and I will post an update somewhere that everyone can read it.
Hi. Do you know if it's possible when you enable the traces to limit it to just one Python process? Or is it going to be everything on the system?
So you can. All of them. So in the case of eBPF, I have to stipulate the process ID that, well, I don't have to, but I can stipulate the process ID that I care about. And in SystemTap, where I had my string, which was the command I was running, remember how it said C? I can go back.
Yep, yep.
See how I have CPython Python there? If you replace that with a process ID, it will only bind to that process ID.
Ah, perfect. Yeah, great.
No more? Okay, to finish off, Chris, I'd like to present you a small GIF on behalf of PyCon Australia for your awesome talk.
Thank you very much. Thank you, everyone.